I'm almostly done. And uh, next week I also do the layouts, study the layout.
But last week you have not checked all cases, right?
Yeah, I check efficiency, some case.
You should check.
Yes.
Okay, Ryan, let's start.
Okay, so this presentation, I have simulated the full system from this following thesis. So here is the full system schematic. So I just only edited the reference ladder part, which is right here. The pulse width control, this part controls TP and this part controls TN. Notice that in this circuit there is no VREF, so TN does not depend on the N. So there are total 3, 4, 5, 6, 7, and 9 delay cells, and each delay cell is 77 nanoseconds. So the TN should be 694 nanosecond for all N. And the VREC value is actually set here. The IC value is set to be close to the VREC value we want. Simulation. So for n equal to 15, as you can see, so if I zoom in a bit, so the TP is 694 nanoseconds as expected, close to, and the VRECT is 5 volts. So because it's here n is equal to 15, so and if we like look at this graph, as you can see, the TN is
Okay.
TN is actually 1.23 microseconds. So if you multiply 77 into 60 is actually equal to this. So it's all right. So similarly, I have simulated for every single case. So this is n equal to 14, 13, 12, 11, and so on. So the TP values are same for all n. So I have not I have already shown the TN value and the VREC value in the pictures. So these are all like same. So as you can see, the for n equal to 0, TN value should be equal to the exactly delay cell, which it is. The efficiency values. So these are the efficiency values that I got. So notice that I have used actually different L for different node efficiency value. My efficiency values are like this. So actually there is a thing to notice that for lower N, for lower L, I have got a good efficiency value. For L equal to 22 or 82, I've got like 0.98. For 820, I got 0.95, 0.96. So, so if this is the case, then why did I use 820 microhenry? That's because of, if you remember, this is a previous simulation that we did. So here, we can see that for higher values, 22 or 82 microhenry actually gives closer to 0. Converges to 0. For example, if we use 22 microhenry here, then we would actually get really close to 0 power. So we don't want that. So that's why for higher voltages, I have used 820 microhenry, even though it's clearly for 820 microhenry, the efficiency values are low. That's it. That's my presentation. Thank you.
So, this week, can you simulate all cases like Ryan do?
Yeah, almost on case, but there's a lot of case.
Yes.
But I'm not like
16,
PPT.
you run all cases, 15 cases, 16.
About 10 cases.
So
I
let's
think
run all simulation and check with Ryan.
okay.
Actually,
So
let me share screen. Actually, Ryan can see my screen.
Yeah, sure. Yeah, I can see.
Actually, Ryan still have issue when compare the VREF perform full system simulation with the output of reactive bias rectifier only. For example, in the case is 5 volt.
Actually, Hong, I have a question.
Yes.
If you like, so while simulating this, the inductor voltage. So can I share my screen?
Yes.
Okay, give me a moment. I have just give me a moment.
Let's share the screen.
Yeah, just give me a moment, please. Okay, so if I go here, so this is basically where I simulated the bias flip rectifier. Here, this V out voltage is actually fixed. So the voltage across this capacitor is actually exactly constant, right? Because of this voltage source.
Yes.
But in the full system, that's not the case. The capacitor voltage is not constant, right? I mean, it is changing. I mean, it's changing slowly, and it doesn't change much if we set like close initial condition, but it is changing. So, is it the reason that like there are different values?
Actually, no, because just a small change. So let me share my screen.
Okay.
So as you see in this power graph, right?
Mm-hmm.
For example, you select simulate VREF here, so it's almost 4.97 volt, right?
Mm-hmm.
Only a few millivolt change, so it's very small voltage change. It doesn't affect the power, almost cost. And actually, I already run for this case. I set internal voltage is in this case in this case 25. So the VREF stable is 4.97 volt, right? I start at 4.9 volt. So in this case, in the beginning, there's no buck converter will not work, right? Because VREF is still smaller than the expected voltage. So buck converter doesn't work until here. You can see the inductor current, right?
Mm-hmm.
The converter work when we will have inductor current. So in the beginning, converter doesn't work. So only bias flip work. So it's like we just disconnect this node, right? The converter doesn't work. So energy is only transferred to the cap. It doesn't take out any energy, right? So if I check the current flow into the cap, we can see it's work like bias flip, right? Yeah, there is some noise here, but anyway, no buck conductor doesn't work. And when buck conductor work, you can see inductor current here. Do you see it? The first phase is current will flow from cap to inductor, right? It build up inductor current, right? And it flows to. So in here is the same. Here is so let's check here. Here is IPJT, right? You can see here is IPJT, right? IPJT flow into the cap. And at the same time, when buck converter work, the current will be taken out by inductor. It take out the current, right? This inductor current this inductor IPJT minus inductor current will be this line, right? So current is in and inductor current is taken out, right? And then, so I will check the current power is transferred to the capacitor when, in the case buck converter doesn't work, is about from let's check from maybe 5 milliseconds until here. About 90 microseconds. So from 5 microseconds to 90 microseconds. So it's about 40 microwatt, right? So around here. So it's around 40 microwatt. And if I check the current in the case buck converters work, so from 100 microseconds until here 800 microseconds. 100 microseconds. is in nanowatt, so it's almost close to zero, right?
Mhm.
So in that case, the current is power is transferred to capacitor and then is all it transferred to the load through buck converter. So that means the input power here is should be 40 microwatt. But when we check here is only 30 microwatt. Right? It is like 30 microwatt. It's quite strange. Engineer, do you have any idea?
I mean, I understood, but I mean, I still don't know why the power is low though.
Maybe some current. We also connect to
But there
maybe
should be
because
no current through the body. Current should be zero for all MOSFET, right?
maybe I think because maybe current loss in here. We connect VREX to other circuit, right? You connect VREX to here.
Mhm.
Do you connect to anything else? Here. I think this also consume power, right? We connect to level shifter
Oh,
and buffer.
okay. Okay.
So I think
That's why P rect is lower than it should be.
so. Okay, I will save this note and check the power then. Do we that all right? We rack only connect. Okay, I will run and check later. So Thái, do you have something to present?
Let me share my screen. Okay, do you see my screen?
Yes.
Okay, real quick, I do some layout schematic from this schematic, and then I do the layout. Also, I check the my simulation before. This is the full system. Then as I checked before, it's also true. For example, efficiency. For example, I use the input with the 2.2 voltage and the V reference from 0 to 3 is 005. Also the let me check. Let me check again.
You check what?
I check
Efficiency?
efficient. Yeah. Um, yeah, I think it's take a lot of time. Uh,
Yes.
Efficiency I check from the 19 to 98, and I check TPUTN is appropriate with the reference that I picked before.
Yes, but one more I want to check is the PREC,
Right.
PREC and the output power from full bridge rectifier alone.
Okay. Which mhm.
You have to run long simulation to check
Oh,
efficiency.
okay. I just capture efficiency. Uh, I took the three example for efficiencies, but let me check uh, the power of the direct.
It will take long time, so let's do other thing first.
Okay.
Check your layout. So let
Yes.
you
Yeah, I
follow
have my
the video.
Yes, I read the file as well, the videos, but do not familiar with layout, so it took a lot of time.
So after layout, we have to check the rule. Do you know that in the video? Tell about that.
Mm, no.
So let me share my screen. Today I will.
Okay. Okay.
So did you read all this slide?
Oh,
Did you read this slide
sorry.
all? Did
I
you
don't
read
receive.
everything?
Oh, sorry. I do not. I missed this PPT. I just read the words.
What?
I just read the job file before, not PPT.
Which file?
Set up it manager.
Ah,
I miss PPT.
you mean this file?
Yes, yes, this one.
So you try to generate layout.
Yes. Firstly, I generate the layout from own source and put them into a frame and then connect them.
First, I will introduce the layouts. So here is the how the MOSFET will look. In the layout, if you open the layout, right? For example, here is NMOS 5 volt, so we will have source, drain, and gate is here is gate in the blue, right?
Okay.
Then did you read about the MOSFET fabrication process?
Yeah, but I know a little bit before the greenhouse.
Anyway, in the process, normally if we use this BCD process, so it will have, if you see here, you will click to routing, okay?
Okay.
Click routing here. So we will have 6 metal 1, 2, 3, 4, 5, 6, okay?
Okay.
So we have bulk is the silicon wafer, right? The so can you see that?
Yes.
It's possible. So we have the wafer is like the bulk of all the circuit, right? And then we have P well and L well, and we will create the MOSFET above the wafer, and then we will have metal 1, metal 2, 3, 4, 5, 6. In our case, it's metal 6, right? So the metal level increase, so the thickness will be increased. If you see here, M1 height thickness is smaller than M2, right? And M3 and 4, that means the metal layer higher is thicker and it can conduct higher current. So normally the metal 6 is used to conduct high current. For example, in our circuit, the high current will be through your inductor, right?
Yes.
Inductor current is normally in milliampere level, right? And in the control circuit is consumed only microampere level. So the current for control circuit is small, and the current for power pack is high. So normally this route will be connected by metal 6, and other control circuit will be used with metal 4, 3, or 1. Okay.
Okay.
So and then the stick diagram is used actually I have been long time. It's like to draw the schematic to for better layout. So if the circuit is complex, for example, please has been long time I don't use this. Stick layout will shows how you connect the nodes in the layout. So let's see. For example, if you see here, for inverter is here is VDD and ground. So VDD and ground metal will be here, and then the output here is here. Here is the output, and the input is here. Here is input. So this stick diagram will be same with how you lay out your metal in the layout. Do you got it?
Okay.
So you can see we can for the same schematic inverter, but we can make two stick layout, right? And then from the stick layout diagram, we can lay out the circuit in two different way, right?
Okay.
So stick layout is used to like to outline how you will lay out the circuit. So first you will draw by your hand the stick diagram, and then you look at this diagram to lay out your circuit in cadence. Okay?
Okay.
So another things is in the layout we will have some design rules. for example, the minimum width or spacing. So in our process is 180 nanometer process, right?
Yes.
So the minimum width of the metal is 100 nanometer.
Bro, but how to train the rule? Like the distance between the wire as well, the width of the wire in the coding. How to train the rule?
What is change the rule?
How we can train the rule in the cadence?
You mean change the width line?
Yeah, just
So for example, I will make a simple layout. In vector here. You follow this step. Step one is create a layout file. Let allow.
yes, I have allowed. I have allowed.
First, I will generate a new layout file. You select layout and let's choose layout XL instead of layout XL. Okay. Layout
Okay.
XL. Then we generate own from source. I think I'll make something wrong. Oh, run XL. Not right. Okay. Actually, this is the old file we generate on from source. Okay, and still we will have N mode and P modes, and then next step is display setting. So you type E to set the space. Here is the space I set. Normally we use wait. Let's check from this layout. No. as I remember, normally we will set 0.05. I think so. I will check later. Okay. 0.05. And then this is little wrong, the setting. I will check the setting and let you know later. So. Next step is generate the body. In here we have body, right?
Okay.
But in the layout, when you generate, the body doesn't have. Here is only brain trust and gate. So we have to Q. You press Q. That's wrong. Q, and then you your here is body type. You can
Visually detach. Okay.
detect body left or right. So you detect left, it should be in the left, and detect body. Okay. And then arrange.
Yeah.
What? You have something to ask?
No.
And then we click here, annotation browser. Okay.
Okay.
Here, it will appear here. So normally I will move it to here. So in layout XL, it will have this browser. In layout X, it doesn't have. So this annotation browser will show how the lines should be connected together. Do you see it?
Yes.
Click here. It will show how we should connect the lines together. Okay?
Okay.
So if you want to move, you click on the MOSFET and then type M, and then left click to move. If you want to save, you can type here or type F2. Then so normally if we want to connect two lines with UP, we type P, okay?
Okay.
Then we can connect together. Yeah, after connect, it will disappear, okay? And then,
Bro, I have a question.
yes.
How can we change the width during the we connecting the line?
So you click on the line, okay?
Okay.
You press Q.
Q. Okay.
Okay, so width, you can change the width, right?
Okay. Okay.
Got it?
Yes.
Q, and you can change the width.
Okay.
So because our process is 180 nanometer process, so the minimum width is 100 nanometer. In here is micrometer scale. So here is the minimum width in our process. Okay.
Okay.
For example, if you change smaller than 180 nanometer, it's
Okay.
you can change it, but then when you fabricate, it will have some error. So let me check. So after finish your layout, we have to check DRC rules and check LBS. So here I will check DRC rule. And so after finish, we will show. So you see it, right? This
Okay.
it's happy width is because we choose smaller than 100 nanometer width, so it will have this error. So do you see it?
Yes.
So
Okay.
if we change to
I got it.
180 nanometer width, let's check again. Run DRC. This disappear, right?
Yes.
But this is a different error because we have not connect this drain and source, so that appear. So let's try to finish this inverter layout. Next is rain, connect to drain. Here, connect to here. And here, front to body. Okay. Finish layout. Let's check. spacing. It have spacing error. Yeah, because it shows that the space in the metal one should be larger than 130 millimeters. So we should make it farther here. Okay. Do
Okay.
you see the circle showing? Do you see the circle around
Yes,
the
I
line?
see. I see. I
Yeah.
see.
So we should make it further to follow the rule. So we will run. Okay, it's done, right?
Okay.
This arrow actually it is the area coverage arrow. This in a small block, we don't need to care this because we only consider this arrow until we lay out the full system. For example, in here is my full system layout. So in the full system layout, we will cover space. So anyway, we only consider this area coverage error when we finish the full system layout, right?
Okay.
Now here is block layout, so do not consider it. Only check the other error. When we finish full system layout, I will tell you later.
Okay.
So so for example, here is this work, my hybrid work. Here is the circuit and the schematic, the top layer schematic. To lay out the full system, we have to lay out block by block because we have to check the rule, right?
Okay.
If you lay out everything and then check, you cannot check all the. It's really difficult to check the rule, so we will make layout block by block. So in here, you have to make a so I draw a symbol like this. So here is in the symbol, inside the symbol will be the on-chip components. Okay.
Okay.
So in my case, the off-chip component will be PV cells, this capacitor, inductor, and capacitor and battery, and this capacitor. Normally, big capacitor and inductor will be off-chip because, for example, in microfarad capacitor, if we do layout, it will be really big size, so it should be off-chip. Okay.
Okay.
So in the schematic, you should draw a symbol and then make your object component out of this symbol. Okay.
Okay.
So on chip schematic will be in this symbol. So you should draw the symbols similar to the circuit. As you can see here, I draw on the symbol. You should draw the symbol like this to check the schematic easily, because later you have to debug and change the parameters. So if you only make a block and doesn't show the schematic, so it will be difficult to see. If you go inside, we will have I will divide the control circuit and the power switches into two. So, for example, in your case, you also need to divide your power switch and PMOS in separate with the other control circuit. Okay.
Okay.
And then and you also need to draw a symbol for the P mode and N modes, because later we will lay out them separately. Okay, make a symbol for P modes and N modes in the buck converter like this. Got it?
Okay.
And then make a symbol for your control circuit and draw the symbol similar to the circuit here. Okay, so
Okay.
so let's make N mode and P mode one symbol, and this bias flip diode one symbol, and then on the control circuit one symbol, and this in red is the object components like I made here. Okay.
Okay.
Okay, tomorrow let's draw the symbol. Do you have time tomorrow?
Yes, I have time.
Tomorrow 9 a.m. is okay. I will continue the layout instruction.
Okay. Okay.
Ryan,
Yeah,
are
yes.
you here?
Yeah.
Are you okay 9 p.m. tomorrow?
9 p.m. tomorrow. Yeah, okay.
Okay, so tomorrow during the day, let's draw the schematic again. Okay.
Okay.
For which schematic?
Your schematic here. Draw the
Okay, this
symbol.
one.
Draw the symbol.
I mean, I have to like symbol and then like, okay, maybe I got it. Okay.
I know how to make a symbol, right?
Yes,
Yeah, I
yes.
also know.
Make a symbol and the raw symbol like the circuit, similar to the circuit like I made here. Do you see it?
Okay.
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 Check my circuit as an example and follow it. Okay.
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 And tomorrow I will continue introduce layout. Now I'm busy, so see you tomorrow.
Okay. Okay. Bro, I have checked the power output. It is the 50 54 power micro.
Let's run other circuit case like Ryan did
Okay.
to check. Okay.
I didn't understand. Like I have to like make symbol for all the blocks.
Right. So you have to make symbol like in here you put everything in this test band, right?
But I have to make symbols, right?
You make a big symbol and then in your big symbol you will divide
feed the small symbols and
yes, for control circuit, one symbol, and for NMOS, PMOS, power state, one symbol, okay?
okay.
Okay.
And in control circuit, you make smaller symbol for it. In your control circuit, you will have power wave control, level shifter, and comparator, other thing, make symbol like this, okay?
Okay. Okay.
Got it?
Okay.
Okay, got it.
And remember to draw the symbol. Don't make only a square, but you have to draw the circuit in the symbol. Okay?
Okay.
Oh, okay.
So it will take some time, but later it will good for debugging and redesign the circuit.
Okay.
Yes, yes.
Okay. Okay, see you tomorrow.
Okay, goodbye, bro.
Okay, see you.
Okay.
Bro.
Yeah.
Okay, okay.
Let me control your computer.
Recording in progress. Recording in progress.
Where your schematic? Yeah, here.
Recording in progress.
Where your schematic? Yeah, here. So you should make a new test band for this one, right?
Yes, okay.
Draw the schematic inside the symbol. Okay?
Okay.
Draw the circuit.
Ryan, can you hear bro who said?
Yeah, but his voice isn't fixed. Like the same problem.
Yes, yes. I don't know what happened.
I think it's a problem with the microphone.
Yes.
Who I don't know why today is so strange. So Ryan, can you share your screen?
Yeah, sure.
Ryan, can you
Okay, so what I was doing was this. So this is the this is what I have done so far. So this is the control circuit, and this is the this is the rectifier, and the driver circuit I haven't made any symbol yet. So this is the control circuit. Then within the control circuit, by the way, the recording is not recording.
Recording? It's still recording.
Okay. So here, like, I have made like symbols for individual components, like the level shifter, the pulse width control, the
Can you
discrete rate
open-
comparator.
Can you open the symbol?
Open the
Open one symbol.
I can understand what you say.
You left click, no double click one symbol. No, double click in yeah, double click. You left click and choose symbol in your view. No, in your view.
No, wait. Where?
Choose symbol. Okay. So how you make the symbol? You copy
The
the
circuit,
MOSFET?
and then yeah, I copied the whole circuit and then just made the white lines green. The wires green, and basically.
I don't know that we can copy the circuit into the symbol.
Yeah, but I did.
Really? I don't know that we can copy But did you try to simulate?
Yeah, the simulation works. I mean, I tried this one, this one.
But did you try to simulate?
Oh wait, actually I can simulate this one as well. I mean, it's okay to simulate, right? There is a warning here. PDD. And where is this coming from? Why is this warning? TP. Where's TP? TP should be here. Here is also warning. I don't know. Oh. This one. Oh. Let's check. There shouldn't be any warning. L2. Period. Oh, all right. It is.
Did you try to run the simulation?
Not with this one, like after making the whole circuit. No, I tried this one. Wait, let me show. I tried this one. This one's with like every block is like symbol, but not the whole circuit. So I
It
tried
still
this
work?
one. Yeah, this one works.
Oh, so nice. So you don't need to draw the symbol, right? Just copy the circuit into the symbol.
Yeah.
Yeah, I think you can save some time.
Yeah, still it takes some time. For example, I could not finish the work yet. I mean, it will take 1 more hour. Hello.
Okay, it's good. So try to finish the symbol and then let me share my screen.
Okay.
Hello? Can you hear me?
Yes. Yes.
I think the issues come from TeamViewer, right? Now, no.
Yeah. Now it's all right.
Yeah, I think because the TeamViewer makes things. So first of all, I want to tell you about the input power PREC. Yesterday, I tell that PREC is only about 30, while the output to the bias rectifier is 40.
Mm-hmm.
And the reason is because we connect VREC to
With other pieces
circuit.
as well.
Yeah.
Mm-hmm.
So power will be consumed by level shifter and buffer because we connect VREC to level shifter and buffer, and also a small power consumed by this register ladder, right? So I calculate the power consumed by here is all the power consumed by level shifter, buffer, and register ladder. So I sum on the control circuit power consumption by control circuit. So now the input power of the buck converter should be PREC. PREC means the power go through this PMOS and some plus the control circuit, right? Hello?
Okay.
Mm-hmm.
Do you understand?
Yes.
So the input power will be equal to the power flow through the PMOS and the power consumed by the control circuit, that
The
is
level circuit,
register
level
and buffer
shifter.
and register ladder, right? So
Mm-hmm.
if I calculate it, P in will be equal to output of bias rectifier. So it is correct for this case.
Okay.
So after finish your writing symbol, let's try to simulate
Mm-hmm.
again and calculate the efficiency again, right?
Okay.
Actually, now the efficiency is not high because more power consumed in this buffer. We use a buffer in my work, and this consume many power because we have not optimized it that. Okay, so low efficiency is not issues here because we have not optimized this buffer yet. So anyway, just check the efficiency again. Okay.
Okay.
And next is we will continue the layout. Yesterday I'm doing layout with Inventor, right? So yesterday we complete the DRC rule check, right? I will check it again. Okay, the area coverage issue will not be considered at this moment. So after checking DRC, design rule check, now we need to check LVS, mean what is LVS? LVS is layout versus schematic. So if you will check whether your layout is correct with your schematic. DRC rule is just check DRC is just check the width and the spacings of your layout, right? But it doesn't check whether you lay out correct with the schematic or not. So we have to check with LVS. So here's schematic, and then we open the layout, and then we run LVS. In here, the run set files I already set, so okay. So we can run LVS. And now here we can see the comparison results. In here it says incorrect port, missing port. So because in here we have pin. Actually, port here mean the pin, right? We have 4 pin, right? Input, output, VDD, and ground. But in the layout here, we don't have any pin yet. So we can update the component. And then we choose IO pin. So for pin, we choose metal, and here showing pin, metal 1 pin, apply all, and then create labels. And use same as pin. Okay, same as pin, okay. Let's click OK. Okay, so the pin appear. So again, we open this browser. So incorrect because we have not connected the pin. Yes. So in here, input is the poly layer, but our pin I choose metal 1, so we need to make a view. To make view, we type O and auto view to create a view. Okay. And move this to PDD and move it to output and move it to crowd. To save, you type F2 to save or putting here. So now you can check again. It still has missing input. Maybe you did not. Yeah, make it longer. So check again. Okay, it's done, right? So your layout is complete after checking LBS. Do you have any question? Hello?
No.
So I already out.
Yeah, it's only two of us in the meeting.
Where I
By the way, like I don't understand the like
what?
I don't understand the layout thing. Like what is layout?
You don't understand what is layout?
No. Like I tried to read this, but
So after layouts, they will make you know the layer, right?
Mhm.
So MOSFET will have short drain and substrate and gate,
Mhm.
and it will create by making the layer.
Okay.
So
And
in
this layer
fabrication
is called a layout.
layout is in here is you are looking in your how to say in this view we are cutting your you are looking at the side view, right?
Mm-hmm.
In here we are like looking at the side view, but in the layout you will looking at the this for like 2D view. So in the layout we will looking from up to down view, right?
Okay.
In this view we we looking just from left to right. So we look in this way, right? So we will see on the layer, but in the layout, we are looking up to down. So
We will not see layers.
yeah, we not see layer clearly, but we can know which layer it is in the layout
Okay, I see.
by seeing the color, right? For example, method one is this color, and then method two. So you can see method one, right? This color, and the method two is yellow, and method three is this color. So in the layout, we see by the color, right?
Okay.
Okay, got it?
Okay, got it.
So you doing layout means you will arrange how the MOSFET will be fabricated.
I see. I mean, I have to like, it's like fabricating the entire MOSFET from the scratch.
Right. So maybe top view. So your chip will be fabricated in a silicon wafer like this, right?
Yes.
So in fabrication, so in a rectangle is one chip, right? So you layout means you are arranging the MOSFET in this small rectangle to be fabricated. Do you got it?
Yes, I got it.
Layout means you place the MOSFET position in the fabrication after that. Okay.
Okay.
So our roles of layouts is, first thing is make your circuit work, right? In simulation, you make the circuit work in schematic, but in the real circuit, it should be work in the silicon, right? So you have to lay it out to be fabricated. Okay.
Okay.
And the first thing is you have to lay out and check the LVS to make sure that this circuit will work. Okay, that is the by checking through the software. And the second thing is you have to make the layout as much as small as possible, right? Because in the real application, we always try to make your system smaller to reduce cost and the space, right?
Yes.
Yeah, so the role of layout is to try to make your chip, fabricate the chip be more compact. So that is the goal we try to achieve. Okay.
Okay.
So I show you layout inverter and check with DSC and LVS. We have a final step is post layout simulation. So after layout, we can run post layout simulation. So something wrong. Okay, I will talk about post layout simulation later, but what is layout? So in the schematic, your simulation is ideal, right? In almost ideal case. And after fabrication, after layout, there will be some parasitic cap and resistance. So cap and resistance will make some delay. So we have to run simulation after layout to redesign the circuit.
Okay.
Do you understand what I mean?
Yes.
So maybe so slow. So to better understand your fabrication, you can read this book in meeting 3, right? Meeting 3, this book. So you can read to understand the views. Okay, so in top view is our layout view, right? And here is side views. So slow. Yeah. Okay, you can read this fabrication to better understand how layout it is. Okay.
Okay.
So we have layout and packaging. Yeah, design rules. I think this book explain better than this PPT, right? PPT is always difficult to read than the book, right? So you might read this book to understand more. Okay?
Okay, bro.
So anyway, I tell you how to lay out an investor and check DRC and LBS. Now it is your work. Your work until Friday is to lay out the power control block. So I already tell you lay out the investor. Now you need to lay out the NAND gate, AND gate, and multiplexer, and the delay cell. In this slide, they already shows NAND gate and AND gates layout, right? You can follow it to do the layout.
Okay.
Okay.
And for layout multiplexer, you can reference this layout. Actually, here is 5-volt layout. I already changed the MOSFET from 5-volt to 2-volt. So you can open this 5-volt 5-volt layout for reference. Okay, and in your 2-volt layout, you have to make a new one. So in the 2-volt schematic, you make a new layout. Right here. Okay, you have to lay out again with 2-volt MOSFET. Okay,
Okay.
lay out again 2-volt MOSFET by using this 5-volt as an example. Okay,
Yes.
do you have any question?
I'm not.
Ryan? Ryan? Hello? Ryan? Are you here?
Good.
Ryan?
Granted, Mika.
Tắt mic á?
And you turn on this.
Ryan, can you turn on microphone? Ryan? Ryan chạy đâu rồi? Chắc thế thôi nhá.
Dạ,
Stop
dạ,
nhá.
dạ.
Okay,
Dạ.
bye. Nhưng
Dạ,
mà
chào nhé.
em đã có phải ru file chưa?
Rú file. Rú anh.
DRC và LVS ru.
Chưa có anh ạ. Cái này như chưa.
Có để gửi anh gửi email luôn nhá.
Dạ dạ.
Bye.
Dạ dạ, chào anh.